Welcome to the ftir.fun Infrared Learning Series. This episode, Ep11 Dispersive Ear vs Fourier Transform. Infrared, why so one? Then close with the checklist. Next, IU, the revolution from 15 minutes to 1 second. Imagine the scenario. In 1960s, all chemistry graduate students needed to measure an infrared spectrum. He carefully placed a copper pellet into the sample holder, started the instrument, and then, today you place your sample on an abstract crystal, press the acquire button, and the complete spectrum appears on the screen in 1 second. If higher signal-to-noise ratio is needed, scanning 32 times takes only half a minute. Next, dispersive infrared spectrometer, the workhorse of sequential scanning. A dispersive infrared spectrometer consists of 3 core components. LPH. Cable 1 is the components of a dispersive infrared spectrometer. Data sources. Labrie, Booker, Ep. Next, I transform infrared spectrometers, STIR, capturing the full spectrum in one shot. 2.1 core idea, replacing the monochromator with an interferometer. The key change in STIR is replacing the prism grating monochromator with a Michelson interferometer, eliminating the need for a slit and sequential frequency scanning. Next, IN 3 core advantages of STIR. The advantages of FIR over dispersive air can be summarized as 3 secret weapons, each named after its proposer. 3.1 filtered advantage, VRILF advantage. Next, IV, SNR, comparison. 4.1 combined SNR improvement. The SNR improvement of FIR over dispersive R is the combined result of the filtered advantage and the Jacquinot advantage. Next, historical evolution. A century from prisms to FIR. Table 4. Key milestones in the development of ear spectrometers. Data sources, Labrie, Jacquinot networks, Jasco, 5.23 generations of ear spectrometers. Next, why did FIR win? Based on the above analysis, FIR comprehensively surpasses dispersive ear in the following aspects. Table 6. Comprehensive comparison of dispersive ear vs STIR. Next, remaining strongholds of dispersive ear. Although STIR dominates general analysis in the mid-infrared, NIA dispersive instruments still find use in the following. 7.1 visible and near-infrared region, VisNear. Next, other advantages of FIR. Besides the 3 core advantages, FIR also has the following benefits. 8.1 low stray light interference. Next, Curie status and future of FIR instruments. 9.1 typical performance of modern STIR. Taking commonly used laboratory STIR instruments as an example. Next, review questions. How does the slit width of a dispersive infrared spectrometer affect resolution and sensitivity? Why is this an irreconcilable contradiction? What is the raw data collected by an FIR instrument? Why is Fourier transform needed to obtain the familiar spectrum? Finally, the drill actualists. Make sure you can recall each item. Core knowledge points. Key points. Dispersive ear principle. Trend frequency by frequency using prism grating. Slit selects wavelength. Dispersive bottleneck. Conflict between resolution and sensitivity. Slow scanning. T minutes. Requires external commeration. Peel principle. Measure all frequencies simultaneously with Michelson. Interferometer. Fourier transform yields spectrum. Coljet advantage. Multiplex. SNR improvement by n times, 30 times. Jacquinot advantage. Light field at 8200 times higher than dispersive, no slits. Hannes advantage. Accuracy. Ham laser self-calibration 0.01 centimeters. Overall SNR improvement. Approximately 100 times. SFT algorithm. Published by Cooley and Chuki in 1965. Enabled commercial STIR. First commercial STIR. DigiLab FTS-14 in 1969. FIR fully replaced. After the 1980s with widespread microcomputers, dispersive exited general analysis. Dispersive strongholds is in MER, process analysis, portable UCL new technologies. That covers the required stencil for this episode. Practice with real spectra on ftir.fun and continue with the next lesson.